Okay, so let's go ahead. I trust everybody enjoyed your reading. Nothing like a little bedtime reading, is there? What we are going to start dealing with is something, and you're going to hear phrases today that you'll hear throughout, and they're sort of apologetic, sort of this is the way the world is, get used to it, that kind of stuff. I mentioned in our intro that we're kind of in an in-between world right now. We are in enterprise networks right now using stuff that Alexander Graham Bell would be perfectly comfortable with. We're using stuff that didn't exist 10 years ago in the same network. In fact, those analog connections, the ones that Bell would be comfortable with, have actually increased in usage since we started using voice over IP because of a quirk of how pricing works out in the world. We'll get to that a little later when we talk about stuff. What we need to cover first is just kind of set the parameters for discussion. And what I'm doing is setting the discussion for this class. First off, understand, like pretty much all the other classes in this curriculum, there is a ton of nomenclature that has to go with this. You're talking about an industry that's been around since 1877. We've made up more terms than you can possibly write down. Some of them still have to be here. We're going to learn those. I'll warn you, there are terms that are in regular usage for voice networking that are the same term that you're used to for data, and they mean different things. Wish I could change it. I can't. I will point them out quite clearly, but we'll deal with those. So what we have to do in this is to remember that what fundamentally we're doing is moving the human voice. What we're doing right now, it's just we're doing it over a longer distance, and we're using electronic media to do it. Okay? Your users don't care how that happens. They just know that when they pick up the phone, they want their voice to come out on the other end. Now, one of the things that we'll have to deal with is that uniquely to voice, I'll put video in there, because two-way video in there, because it's the same sort of situation. Unique to those applications, your end user actually is a person. You can't always say that about data. You know, I can move data across the network and have it automatically stored in a database, or go to a computer and display and wait for me like this slide is right now. When I speak into a telephone, my assumption is that you hear that. My assumption is you hear it instantaneously. Practically, you hear it nearly instantaneously. And it's that word nearly that gets us into trouble. Network requirements for real-time media, voice and video, live, two-way, are very stringent. And they're stringent not because it's hard to move that stuff across the network. It's not. It's trivial. What's stringent are the person, the user requirements for that. For example, have you ever watched CNN or something when there's breaking news and they're doing a satellite link that they've had to set up real fast? And you see the anchor, and they ask a question, and then you got this poor guy out in the field somewhere holding a mic. The anchor asks the question, and he sits there just looking dumb for about a second and a half. What's going on? Well, there are all kinds of tricks to get around the delay, but the laws of physics, the speed of light, say that that signal can't travel any faster than the speed of light. It's about a 3/4 second one-way trip through a satellite. When they set those links up fast, they don't have time to pre-delay it or any of the other fancy techniques they use. And so what you're looking at is, I'm the anchor, I say something, you're the guy on site, you hear it 3/4 second later and reply, but then there's another 3/4 second before you get it back. So there's a 1.5 second delay. Now for broadcast, we'll deal with it. It's actually kind of hard to get used to. It's particularly tough on those people in the field. Satellite phones get the same thing, although the delay is not as long. They are surprisingly hard to use because I say something, and my assumption, being a person, is that you hear it immediately. Well, that's not the case. That's not the case. You hear it after whatever delay there is through a system. In both of these systems all of the systems we're talking about, there is some form of encoding going on. There's either analog encoding, which is actually pretty fast, and there's digital coding, which we're going to talk a lot about because that's mostly what we're going to deal with. Digital coding takes time. From the time I speak into that device until it's coded to data that I can send across the network, there's a finite amount of time. You've all played with ping, testing networks. What's one of the things ping tells you when it gives those response back? What's one of the things it tells you? How long it took to go. Are they always the same number? No. How widely do they vary? Fast network's a millisecond. Slow network might be 400 or 500 milliseconds. Well, what's 500 milliseconds? It's half a second. That's a long time. Let me put it into perspective for you in terms of how the psychology works of this, and it is psychology. We humans don't like delay, period. When I say something, I want you to hear it right then. We'll actually put up with it. We actually don't notice it much until you get to about 25 milliseconds. Depends on which textbook you want to look at and what study you want to look at, but it's around 25 or 30 milliseconds before we really notice much. We'll actually tolerate it up to about 100 milliseconds. That's a tenth of a second. Above that, and this happens automatically. It's not that people think about it. It's just we change the way we talk. When you have a discussion with somebody, you ever talk at the same time? Sure you do. It's part of the way we communicate. And we do it on the telephone. Once you get the delay to about 100 milliseconds, that fundamentally changes. We slip into two-way radio mode. I'm going to talk. I'm going to do a big, pregnant pause, and then you're going to talk. So the first thing it does is slow down our communication. The second is so much more formal sounding that you don't tend to communicate the same way. That's part of the psychology of it. So we'll talk about the $5 term for it is latency, network latency, and we'll talk about that actually in the latter part of the semester, but I'll mention it as we go along. The other thing that is a problem and uniquely human is if we have latency, I want it to be the same all the time, or at least all the time during one call. And the way networks work, IP networks are designed to move data, right? My web browser doesn't care. It doesn't care about delay in the first place, and it sure doesn't care if the delay changes from packet to packet to packet. I do. My brain doesn't like delay, but it can get used to it. What it can't get used to is delay that changes all the time. So by golly, if it's going to be 30 milliseconds or 70 milliseconds or 150 milliseconds, at least make it the same all the time. And that's a surprisingly hard thing to do. Think how we design networks. We design networks, let me finish the thought and I'll get right there, Dan. We design networks to move data as quickly as possible. So if I can reduce delay by going another path, that's what I'm going to do. But that aggravates the very problem I'm talking about. So we've got some issues with network design. Yes, sir?
I know with the satellite, it's latency, but with video phones, it's more bandwidth, isn't it?
Bandwidth affects it. Excellent question. Let me give you the short answer on it, and we'll get into that a little more when we look at coding. The short answer is when you code anything, video, audio, it's more visible on video. What you're doing is taking an analog signal and converting it to data. You guys know that. Okay. I can do that a couple of ways. I can do it with very high quality, which means I take a lot of samples and a lot of bits per sample, and I generate a very large data file to move. Okay? For a given network bandwidth, larger files take longer to move than smaller files, right? If I have to move a megabit, I'd rather move it across a network that moves a megabit a second than a kilobit a second. Okay, at the same amount of data. And that's what you're talking about. If I use more compression, I throw away data, but not to the point where I can't reconstruct it. I make a smaller signal, but the perceived quality on the other end is not as good. And that's the game we play with video or with voice. When I use smaller signals, it doesn't take as long to send the data, therefore the latency is shorter. When I use, excuse me, I've got a tickle. When I use higher quality signals, and I'm being very fast and loose with the nomenclature here, when I do higher quality signals, I have bigger amounts of data to move, therefore it takes longer to move it across a given network. So yes, you do see that effect, but it's not directly because of bandwidth. Bandwidth is the secondary issue.
It's just the way it's set up versus the satellite.
Yeah. Now, good point, because one of the things that you'll do in this class that is not covered in most classes is something called traffic engineering, which is how much bandwidth do I need for the amount of traffic I have to move. Bandwidth is cheap right now. And so the way a lot of times these networks are designed is you just throw bandwidth at them. You know, I need 30 megabits, fine, I'll put 100 in. You know, it's that kind of thinking. I've watched the pendulum on this swing 3 times. We're on the 3rd time back for me now, from bandwidth being highly expensive to dirt cheap to expensive to dirt cheap, and it changes on major carrier technologies. You know, when we went from modems to cable, or to ISDN, it sped up. When we went from ISDN to cable, or the kind of networks we have now, we had the same swing. It's about to swing again. So, excellent question. So anyway, where we're going with that is you have to realize that our industry is in transition. You're going to see these old technologies for a while. They'll fall off the back. You'll come back in 10 years. We'll laugh about it. Well, actually, I won't be here in 10 years, I hope. Awesome. I'm 54. I really don't want to be here when I'm 64, much as I like you guys. You probably won't see any of the traditional network stuff. There won't be a need for a voice class, particularly, because really what you're talking about then is voice is just simply another application that has some sort of unique requirements, but not that big a deal. There won't be a need to treat it as a separate class. Now there still is. So. Okay.
When it's not treated as a separate class,
Mm-hmm.
would the landline still be around at that point?
If by landline you mean analog circuit switch loop, no. I bet you won't. I don't think you'll see analog circuit switch loops. I know you won't see them 10 years from now. I'm betting you won't see them 5 years from now.
I have to wait 5 by 2 or something.
I'm actually, it's interesting. You anticipate something I ran across that I'm going to post just for you guys to read. It's an article that looked at penetration of landlines. In other words, how many landlines are installed. What do you think it's been doing over the last few years? Yeah, we've lost 48% of the install base of landlines in less than 5 years. So it's an interesting article I put out. It's not very long. Okay, the fundamental issue we deal with, one of the fundamental issues, but it is a very fundamental one, that we deal with in voice is the fact that there are really 2 completely, almost diametrically opposed systems for accomplishing this end-to-end voice communication. The original voice networks were point-to-point. I had a phone on my desk. It went directly, don't pass go, don't go through a switch, don't let anybody else do anything, to a phone on your desk. If you wanted to talk to 2 people, you had 2 phones on your desk. Remember your 133 mesh network? If I have 2 endpoints, how many connections do I need? N times n minus 1 divided by 2, so I need 1 connection. If I have 3 endpoints, how many connections do I need? N times n minus 1, 3 times 2 divided by 2 is 3. If I have 4, see what's happening? How many endpoints do I need if I have 100? endpoint. How many connections do I need if I have 100 endpoints?
I read something like 10,000.
It's 9,999. You don't need a connection to get to yourself. That's it. That's assuming they run in both directions simultaneously. That's the way the original phone network was built. And to be fair, it was actually put in place as burglar alarm systems, very simple burglar alarm systems at night, and during the day they strapped a microphone and a speaker across it so you could talk. That's really what they did. A guy named Puskas, I never can remember this guy's name, being a West Kentuckian, Theodore Puskas, who actually worked for Thomas Edison, came up with the idea of an exchange. And it was to address this very problem. They were building in New England, they were building telephone networks with analog phones, you know, and it was quite the thing for rich business people to have phones to talk to people and all that. But it was a mesh network. So I'd have 4 or 5 phones on my desk and 4 or 5 lines fanning out from where I am to go to wherever it needed to go. What Puskas did was simply take one phone, run it back to a central point. You know, you guys are way ahead of me on this. Ran it back to a central point, but then, this is the smart part, then he came up with a way to allow one line to be connected to only one other device, but to be able to change that. The thinking was, well, you're not going to talk to more than one person at once. He obviously hadn't been around in cell phone days. You're not going to talk to more than one person at once, so provided I can connect that one subscriber line to any other subscriber line, I'm golden. And that's exactly what he did. If you think about that, what you're going to end up with is a branching star network, right? Everybody in the geographic area is going to go to the same central point where we're going to switch between them. You're more likely to talk to somebody close to you geographically. I'll leave the personal relationships out of this. Geographically, you're more likely to talk to somebody close to you than further away. I'm more likely to call my friends here in town than somebody in Los Angeles or somebody in China or somebody in Europe. That's the thinking. But I take those stars and I bring them into a central location. And we get it so we can piece together a path between any two. Because that's actually what we're doing. Notice this first term, circuit switched. You guys are learning this actually backwards from the way it was developed. You guys have already learned packet networking. You know packet networking backwards and forwards. That's a fairly recent development. I mean, the people who developed packet networking are still alive. It was developed in the 60s. Actually, they're a heck of a lot of fun. A guy named Vincent Cerf. If you ever see a webcast or something, when do yourself a favor. He's a scream. Circuit switching means I build a physical path, or I build a path, I should say. In the terms I'm using today, it's a physical path. I build a path between you and me, and that path is in use for our call for the entire time we're on it. Nobody else can use it, can't share it, it's just us. When we're through, we tear that down, and then somebody else can use that path. That's circuit switching. There are advantages and disadvantages to it, but it is a dedicated connection. The other way of doing this, of course, this is the circuit switching is what Puskas developed, and it's what everything used in voice networking until the 60s. It's what the telephone companies used well into the 80s and really into the 90s. Okay. The other way of doing it is what you're used to, which is packet switching. Instead of building a dedicated path end to end, I take my data and I mark it. I address it so I can send the data in smaller pieces, packets, individually across a general purpose network. And each packet, you know this, finds its way across the network individually. Well, look what happens, though. If I have two phones, red dot and green dot, just to keep them separate, I code that data, I individually address it for where it's going, and then I put on this general purpose network. Each packet routes individually. When I get to the end, green packets go to the end point of the green call. probably the first time we've ever had a green call in the telephone network. Red packets go to the destination for that. I'm sharing that middle network, and there may be a lot of other stuff in there. Okay, remember our discussion of latency? What's going to happen to my latency when I have other stuff on this connection trying to move data? As I put sorry about that online class, your ears can recover as we go along. As I put more and more devices on a single network segment, what happens to my performance? What happens when you're on a really heavily loaded network trying to download audio or a website or a movie or something? Slows down, sure. Why? What's happening?
There's more collisions.
There are more collisions, but that's not actually the first thing that's happening. You're right, there are more collisions because of this same thing. How do, I'll use Ethernet as an example. How does Ethernet share bandwidth?
Does the router have to take more time to route to the network?
It does, and that's a small part of it, but that's not the major issue. Forget routers on a single network, just an Ethernet segment. As I add host computers, what happens? What does Ethernet have to do? How does Ethernet work? How does it share bandwidth? Okay, the protocol is called? Oh, he's asking for, yeah, CSMACD, Carrier Sense Multiple Access Collision Detect. Now, Ethernet is the most widely used LAN protocol. So I'll use it as the example, and then we'll look at the wide area net side on it. In Ethernet, since what I'm saying, Carrier Sense Multiple Access, is all the devices are going to use the same network. That's the multiple access part. Carrier Sense means if I need to transmit, I listen to the network. And I can't transmit as long as somebody else is using that network. Once it's quiet, and it actually has to be quiet for a minimum amount of time before I can send, I can transmit. Well, while I'm transmitting, nobody else can. Okay?
Kind of like a traffic jam.
Yeah, it's an almost polite traffic jam, basically. Now, what happens in that process? Think about a network with only 2 machines on it. Is there going to be much contention for bandwidth? Probably not. You know, I mean, I'm going to send stuff to you, you're going to send stuff to me, but in computer terms, we're waiting forever before one of us does something. As I add machines to that network, more and more devices that are occasionally going to have to send traffic, what happens to the probability that any particular device can transmit at a given moment? Probability that it can transmit drops, right? As I add more devices, I've got more devices contending. Remember, this is contention-based networking. I've got more devices contending for the use of the network. So the chance that any one of them is going to be able to do it at an exact moment drop. Okay. There are similar protocols used in wide area net. We'll dig into some of them. But basically the same result happens. As I add more devices on that network, it becomes less likely that any given device can transmit at a given time. Now, bringing it all back around to the first, remember latency? Latency was the delay from one end of a call to another. If I'm having to contend for bandwidth, that means my network interface in my phone can't transmit whenever it wants to. It has to wait. I increase latency. And since I'm trying to jump on the network as soon as it comes available, my latency varies. So I've just introduced jitter. Okay, that's the fundamental issue we're dealing with. There are ways to deal with it. We will have the joy of playing with them. But for now, realize that as we load this, the more users we put on this, the more trouble we have with latency and jitter. Okay, I'll leave it at that for now. Okay, in a data network, you guys have already done this, 241 in particular, you looked at, you know, how you have LANs or multiple LANs and how they share a connection to other places. We call them LAN, local area network, and WAN, wide area network. But basically what you're talking about is a router allows any device on that network to share a connection to the internet to go other places in the world. Okay? You've all done that. You usually set the router interface on the local network as your default gateway. What's default gateway do in words? Don't give me a technical IP address description.
I think it means that if it doesn't know where it goes, it sends it there.
Exactly right. Default gateway is where an interface sends traffic that it doesn't know what else to do with. Now, the default gateway may not know what to do with it. And what's it going to do? It's going to send it to its default and on and on. When we talk about voice networking, we have those same functions in play. You know, I have lots of users in my enterprise, you know, 50, 100, ever how many people I have. I can't afford to give each of them their own connection to the internet. I make them share one. Now, it might be a pretty big one. I might pay a lot of money for it, but I'm making them share one connection. I do the same thing with my voice connections. I'm showing a circuit switch diagram in this for voice at the bottom. And if I have connections from my network out to the world, I'm going to use a shared connection to the PSTN, and everybody's going to contend to use it. Now, there are a couple of terms you're going to run across. I'll use them regularly in here. On-net devices are devices that are directly connected to your enterprise network. You know, you are directly responsible. I'm not saying they're connected to the same network device, but they are connected in, they don't have to cross anybody else's network to get there. It can be a little hard to see when you talk about wide area nets because you do cross carrier networks, but you do something called private networking where that appears to be a private net. We'll look at that when we dig into wide area net more. But on-net devices are those that you directly handle all the traffic for. Off-net devices are everything else. They're all the devices that do not directly connect to your network. Okay? What we're talking about is that on-net devices can communicate among themselves really however you want. Now, what you've played with in this is private networking, right? Usually you set up 192 or 172 ranges inside so that you can use an enormous amount of IPs. You don't have to worry about public IPs. To go out to any place else, you have to use public IPs that are routable on the main internet. Similar thing applies in the PSTN. I can have private connections all day long, and I can number them any way I want. If I use the PSTN, I have to use official, quote, unquote, numbers. And we'll talk about how that comes along. But basically, you're talking about private addressing and public addressing. Same scheme exactly as you dealt with in IP. You're going to find a lot of parallels, and I'm trying to draw them very clearly. Now, in a data network, the router is what makes that shared connection work. Remember the bottom line definition of what a router does. It keeps track of where networks are. Now, we don't usually think of it quite in those terms, but if you think about what you program a router to do, you tell it about every locally connected network, and you define the IP range, the logical network addressing for those local networks. And you define it in terms of ranges, right? I don't put every single IP for every host on my network in there. I write a range, you know, 192.168.121/24, something like that. I'm also going to write rules that tell me how to get to other places that I need to go to. If it's a place out on the internet that I use a lot, maybe it's a data center that I back up data to, I'm probably going to put a specific route in there in my router so that I always know how to get there. You can argue that among implementations, but you know that's one use of a route table. Similarly, I don't have to tell the router specifically how to get to every single place on the internet. There's a method in place for my router to find how to get to some place it doesn't know about. That's that default gateway action. Okay. In voice networks, we do kind of the same thing, but there are actually two devices that do it. First one is called a PBX. And the $5 term is Private Branch Exchange, but PBX is pretty universally the way it's referred to. A PBX is just simply a telephone switch that is owned by the enterprise instead of by the phone company. It can do everything the phone company switches can do. It's just owned by a company. So what you do with the PBX is you have all your private stuff inside, and you put phone numbers on them, and you figure out how you want phones inside to be able to communicate, on and on and on. And you figure out ways to send calls that need to go off net to the PSTN.
So that's a telephone, enterprise phone telephone switch?
Private branch exchange. The other way of doing this is something called a key telephone system. Key telephone system is, excuse me, just a second. So yes? Okay.
Yeah, for now.
Okay.
We've got a 48-hour period.
Okay. So a key telephone system is another way of accomplishing this, and they differ in kind of a fundamental way. A PBX is a switch. It can make switching decisions, routing decisions. A key telephone system isn't. Let me go ahead and show you a key telephone, and then we'll back into how this works. You may have seen these. They're still around. You still see them. Sometimes if you go into a business that's been around forever and a day, you may still see some of these. But these are the phones that they look like old style phones, except they have this row of buttons across the bottom, and you'll hear, Bob line 2 or something. And what Bob does is punch line 2. Here's what's going on. Each of those individual lines, notice the KTS has 2 connections. It could be 3, it could be 4. They're individual connections to the telephone network. I'll come back to what the PBX has. Each one of those will show up on a button. Basically what you're doing is you're letting the user select which phone line is connected to their phone. Think about your grandparents' phone. I used to say your parents' phone. I realize that probably doesn't work for most of you guys. Yeah, you made me feel old. Think about your grandparents' phone at home. When somebody calls your house, every phone in the house rings. They're all connected to the same loop. You have a pair of wires, the phones are connected across it, so when somebody calls, every phone on that loop rings. They're all connected to that line. Okay? In a key telephone system, you have multiple lines coming in, and you put all of the lines on each phone, and the user selects which line they want to use. So basically, yes, there's a switch involved, but the telephone network doesn't know anything about it. The telephone network is going to route calls to a particular line based on the phone number assigned to that line. There's no switching happening on the local site. Okay? Let's back up. Lines have, that's a term we all use, but actually you have to be careful with that term when you're actually dealing with setting these systems up. Lines specifically connect phones to switches. So when I say I have my home telephone line, I'm saying I have a connection between my home telephone, the one, I pick it up and use the phone. That line connects directly to the telephone company switch. its identity, the phone number associated with this, is programmed into the switch. It's a port on that switch. You ever noticed how port-centric Linux is? Everything in Linux is a port, right? Linux was designed off Unix. Unix was designed to run telephone switches. Everything's a port. That's why. Now you know. So what we're doing in this is I'm simply extending multiple lines to the site and letting people select which one they use. Now, let's say I have those two phones down there and I have two lines coming into that key system. If one of those phones wants to call the other, it selects a line and it has to dial the number of the other line. And what will happen is the call will leave that site, go out to the PSTN, be routed because you dial the number of the other line, and it'll come back in the other line. So I've tied up both of those lines that I'm paying for to make that one call. In other words, all the switching happens in the PSTN. You okay with that? So those are just lines. From the phone company's point of view, there's nothing at that site but telephones. Okay? The other way of doing the connection is how we do it with PBXs, which is something called a trunk. A trunk is a connection between two switches. It's not just a connection to a carrier. It's actually a connection between two switches. In fact, it doesn't even have to go to a PSTN switch. You can have private trunks that connect PBX to another PBX. Okay? The difference in a trunk is you can associate it with more than one telephone number. So I can put 100 numbers. I can tell the PSTN a range of 100 numbers that are associated with that trunk and say, essentially what you're saying is, if you get a call for one of these numbers, send it to this trunk. Since it is a trunk, the PSTN knows that there is a switching device on the other end whose job it is to get it to the right phone. Okay. What do lines connect? Switch to telephone. What do trunks connect? Switch to... There you go. Okay. We'll deal with both of these. However, I'll tell you. The key system, as I described it, is actually pretty old technology. If you try, you can probably find one. I don't know of anybody that's installed a new one in at least 20 years. What you do see, and what people will refer to as a key system, is a programmable system that mimics that shared line. I want to push a button and get line 1 or line 2 or line 3. It mimics that operation because that's what people at that particular site are used to. Okay? Those devices actually are PBXs. They're just making it look like a key telephone system. Is that confusing? Yes. That's why we're not going to use them in here. Okay? We're going to stick... Everything we talk about or do in the lab is going to be based on PBX thinking. Okay? Probably, if you go out in the world and somebody says, oh, we have a key system, I would bet you $10 that what they actually have is a small PBX programmed to act like a key system. Okay? So we'll do PBX in here. We will use lines because you can make a PBX make use of lines. But we're not going to deal with mimicking a key system. Okay? So everything we do from here forward is going to be PBX. Okay. The other thing we've got to deal with, let me see here how time is doing. Okay. When we're talking about these two basic technologies, and again, what I'm trying to do is just kind of set the parameters for discussion as we go through the semester. When we look at circuit switch networks, or PSTN, remember that what we're doing is building a dedicated path for each call between the endpoints. And for the duration of that call, that path stays in place and is only used by the endpoints on that call. Okay? So here I show kind of the perfect world. 3 phones on each end and three trunk connections. And those are trunks, right? Because they're connecting switch to switch. So top phone picks up, dials the number for top phone on the other side. That path is set up. It's local loop. The switch says, oh, I need to go across this trunk connection to the other switch. That switch says, oh, that is destined for top phone. We'll look at how the addressing works later, actually pretty soon. Middle phone goes off hook, dials the number from middle phone on the other side, connects across the trunk, bottom phone to bottom phone. Okay. At that point, I've used up all my network bandwidth, right? 3 trunks. So if I had 4 phones, what would happen if I tried to connect 4th phone to 4th phone? Can I make the call? No, I can't. There's no network left. That's the problem. That's one of the problems with circuit switching. If you're going to summarize it, in circuit switching, bandwidth is exclusively allocated. There's the $5 term for a dedicated path. We allocate bandwidth exclusively to a single call. We'll get into the whys of the next line a little later, but basically that is 64 kilobits per call. And the sharing is by allocation of circuits. In other words, I'm going to assign the use of this particular point-to-point path to your call, and that's how I share bandwidth. I have 3 phone lines, 3 times 64 kilobits worth of bandwidth, and I'm going to assign it in 64 kilobit chunks. The 4th person to come along is out of luck. Okay? Which means the capacity of that network is proportional to the number of trunks. Notice I didn't say limited to. I've shown a perfect example here. 3 phones, 3 trunks, 3 phones on the other end. Realistically, if you have 2,000 users, the university has roughly 3,000 at any point. I'm not going to support 3,000 trunks. We have about 3,000 users. We have 100 PSTN trunks. And that works. We'll talk about the whys on that later. But basically what you're doing is playing a statistics game. How likely is it that of all these users inside, how many of them are going to need to make calls that use my trunks? Okay. Remember, you're more likely to call somebody that is geographically close than somebody that is geographically remote. Okay. So we're playing a statistics game. So if I'm going to increase my capacity, I'm going to have to increase the number of trunks. Okay. In packet switching, you recognize a network, a couple Ethernet segments, router, matrix out in the middle, however your wide area networks. In this case, we're doing what you guys are familiar with. We're allocating bandwidth when, when an application needs bandwidth, we're giving it bandwidth. It actually has to contend for it, but we allocate it based on, the device only tries to use bandwidth when it has something to transmit. Okay? Second one, codec is a contraction of coder-decoder. This is where you do that analog to digital conversion and digital to analog conversion. So on one end, I take analog audio, code it, send it across the network as a digital signal. I receive the digital signal, decode it, put it back as analog. We'll look at the process later. Different codecs, different processes for doing that voice coding will end up with different bandwidth. And that gets back to the question Daniel asked. Can I change network performance by changing bandwidth? Yes, Daniel is asking it from the point of view of can I make the network bigger, and that'll certainly help. But you can also achieve about the same thing by keeping the same network and making your signals smaller, right? And that, as long as my network is bigger than the signal I've got to get across it, I'm going to have pretty good response. Different bandwidths. Codecs are designed to accomplish different things. Some of them are designed to have extremely high quality audio. The cost there is that you're using a lot of bandwidth, so I've got to move a lot of bits across the network. Others are designed to be very bandwidth efficient. They may be using very narrow satellite channels, for example, or some reason that you have to use a small amount of data, and we're willing to sacrifice aural quality for that. We'll look at codecs closer a little later. And the sharing of that network bandwidth is by packet switching, which you guys are completely familiar with. We're talking about doing exactly what you know. Okay? The more applications you put on a network, at some point you're going to start seeing applications having to wait for network bandwidth. That's what we're talking about here. So the bottom line on that, when we talk about network capacity, is the network capacity is proportional to the capabilities of that software codec. If I can code for a given size network, if I can code audio into a smaller data stream, I can carry more calls. And that's a function of the codec. Now, looking at the bottom one, I've shown it. It doesn't look that much different than the PBXs, but the difference is, since we're doing packetized transmission, and since each of those packets is individually addressed, I don't have to think about those connections. I don't have to know what the layer 2 connections are. I can just think of this whole thing as a cloud. In circuit switching, I have to know very accurately what the physical connections are in my network. In fact, in a lot of cases, I have to go in and hand program them. Okay? The bottom one, that whole network on the right, is just simply an IP address. You know, I send it to that router and say, here, make this go where it's supposed to go. You know, that's all I have to worry about it. And the packets may take different paths between them. Again, you guys have dealt with this. I keep beating on that you've dealt with this. And what I'm trying to do is to make you realize the voice, with the exception of having to deal with latency and jitter, is just another data application. You've already done this. Okay? Now, that's not to say you're not going to have an uphill climb in some areas. You certainly will. There's a lot of new stuff to learn here. You're going to have to figure out that there are two uses of the term switching that have very little to do with each other. So we'll get to that. So what I've been showing you through these slides is just kind of a way to think about our world. We have two not quite opposite ways of accomplishing the same thing. The goal is to get my voice across a network to you so that you hear my voice. And we've got two pretty different ways of accomplishing that. Unfortunately, we don't have the option completely of choosing between them. Right now, you have to deal with both of these. Realistically, your enterprise network is going to do this. Everything inside your enterprise, odds are, is going to be voice over IP. If you're at a place that's been around a while, you may have some legacy stuff that's circuit switch, but it's going to be on the way out. Nobody's going to buy a new PBX, circuit switch PBX. On the other hand, at least for now, you can't get everywhere you need to go in the world using voice over IP or packet switching. You're going to have to talk to the public switch network, which is a circuit switch world. Like I said, that'll probably disappear in the next 5 to 10 years. My bet would be closer to 5, but we'll see. But for now, you're going to have to deal with it. Okay? You okay with that? And so when you ask me questions about how things work, more times than not, I'm going to give you two answers, at least. And the reason is, it's not an either-or kind of thing. It's an if-then sort of answer. If you're talking about going somewhere that has this kind of support and this kind of network and this kind of equipment installed, then the answer is. Okay, that's the way you have to deal with things. Okay, that's that presentation. What about the reading? Did you guys have questions from the reading? Anything that from the reading that you can't tie to this? Don't pack up yet. We're not through. Anything that seems foreign out of this applied to the reading you've done? It makes sense pretty much? Those two chapters are kind of an overview. The first one really is just kind of setting the stage like I've done here. It just does it differently. The second one is really kind of looking at the idea of how you move circuit switching onto packet, if you needed to boil those two chapters down. Let me ask you this. Can you think of any limitations for the voice over IP method? Anything that PSTN is going to be, or circuit switching is going to be just superior on?
So you can be more secure.
It can be. It can be because you have to, in circuit switching, you're going to have to get to that same physical path. Now, in the same breath, I'll say you have that same security because almost all your IP stuff is going to ride actually that same physical network, so you're in the same place. But yes, it could be. Anything else? Think about latency. Talk to me about latency.
You have to have, you're going to put it on a system that has to have enough bandwidth available to make sure latency is low, because if the data stuff takes up too much room, your latency on your voice over IP might go up.
Right, okay. In an IP world, my voice is contending with everything else that's on that network for bandwidth. What about in the circuit switch world? Am I contending with anybody for bandwidth?
You are, but it's just can't.
There you go. I am contending, but once I get the bandwidth, it's mine for the duration of that call. So with that in mind, talk to me about latency. If I have my own bandwidth, and I'm not contending with anybody, once we set up that circuit, that path is in place. And there are exactly two of us on that network.
It'll be consistent as well.
It's going to be consistent, and it's going to be very low latency. That's actually the advantage of circuit switching. It has very low latency. Port to port is usually under 10 milliseconds. And it is rock solid.
Do they try to handle some of the voice over IP by dedicating certain ports to it?
They don't dedicate ports. What you do is, you guys remember quality of service in 241? You use QoS to characterize traffic, and you make real-time traffic, voice or video, more important. And I'm using generic terms because I don't want to start throwing terms around loosely. You make voice more important in terms of network access, and we'll dig into that. What about being able to? What about being able to survive failure of a piece of equipment, like a router or a telephone switch? Yes, John.
If the trunk failed, that connection is gone. Using the packet switching, I would imagine that it uses line of that route.
What happens if this router dies? Can I still get traffic end to end? Yeah, I've got two other paths. And that's the advantage of packet switching. Now, do I have single points of failure in this network? Yeah, I do. If I lose the routers connected to these LANs, then I'm still not going to pass traffic. But there are ways to deal with that in IP. How do you connect how do you make two internet connections to the same LAN? What do you use? Oh, he's asking LAN questions. BGP. BGP lets you use multiple connections that route back to the same network address scheme. So I can actually put two routers on there going to completely different networks that address the same system and deal with it that way. So I can make this a very resilient system. What you get to is kind of a fundamental difference, and it's the build it like a tank versus just build a lot of them. Telephone switches are massively redundant. They have redundant power supplies. They have redundant processors. They have redundant input and output. They have redundant this, redundant that. The databases are backed up. You can literally go in a well-designed switch. You can literally go in, physically unplug the primary processor, and it won't stop. They have redundant routes. I physically unplug my multiplex trunk connection, and it'll route around to another one. They're capable of doing that. The price is I'm having to build this in discrete segments. So I buy this stuff in some multiple of interfaces. Maybe I buy a card that has 8 trunk connections on it. What happens when I need the 9th trunk or the 9th phone? I've got to buy a whole nother card. It was called the golden telephone. It's the one that had to be made of gold because that's the only way you could afford it. How do I expand IP-based systems? How do you add more web services if you've got a web server up and you're getting more traffic than one server can handle? What do? Put another server up offering the same service, put a load-sharing device in front of them, and what happens? The load-sharing device sends that traffic to whichever one of the servers can handle it at the time. I can do the same thing with voice traffic. Okay? So I can grow this. Also, I can look at that top diagram and tell you precisely what the maximum number of calls I can put up between those two switches is. 3, right? I've got 3 trunks, therefore there are 3 calls. Next. What's the limit on the lower one? And what would determine the limit on the lower one? Okay, codecs and bandwidth I heard. What you need to realize, and you're all just about there. In an IP network, a trunk connection, from my point of view, or a call, let's say, the connection between us is really just the bandwidth I need to make sure I move enough data for you to get audio consistently from me. So if I choose a low bandwidth codec, I can put more calls on. That's one way to do it. The other thing is this is packetized. If I'm not talking, I don't send data. Okay? It's called silent suppression. In trunks, how do I allocate that bandwidth? For the call. Once I give it to you, it doesn't matter whether you're talking or not. As long as that call is active, you have that bandwidth. So there's actually not a hard limit to the number of calls I can put up across this network. Now, I can give you numbers that will say absolutely this will make it fail, but I can't say you can have exactly 5 calls going across it because it depends on how much you're talking. Do you talk very fast and no spaces? Do you talk like us from West Kentucky? You know, that kind of thing. So, and we'll look at that more when we look at traffic engineering. Okay? You okay with this? Is this okay for a... Okay, I will have an assignment up here in about another half hour. It'll be due by 8 a.m. Friday. It's just an exercise over what we've covered today. See you guys.